former university lecturer at the University of San Agustin teaching pharmacy courses. So one equations that I find it hard to find is the percent purity. So now let's discuss one method that will make you use this percent purity equation, and that method is your titration. It's a method of testing the purity of a substance. Now in this video we will discuss three things: what is purity, why are we so interested with it, what is titration setup, and how do we exactly solve for the purity. Now, in reality, when you make your drugs, your active ingredients, the ones that you put into your capsules or make into tablets or other dosage forms, you synthesize it in your laboratory. Now, when you make these cool chemical reactions, so for example, your paracetamol, it comes from another substance, in this case, para-aminophenol, and using acetylation, you will be producing this substance. In some countries, they call it your acetaminophen. Now, when you do synthesis, you get the substance that you're really interested with, your paracetamol. But there are some cases wherein you will be producing what you call your byproducts. And these byproducts, you're not really benefiting from them. Some even would harm you. And you call them your impurities. I want you to remember that it's pretty normal for you to have impurities no matter how good your process is. It's really expected. But what you have to remember is this: when you make your medicines, your monograph, okay, I'm not going to explain what a monograph is, but basically it's a document which will describe the purity, the quality of the medicines. It will tell you what impurities are allowed and at which limits. So not all impurities are allowed. Some impurities are so harmful, we don't want them. And some impurities are expected, but they have to be kept at a limit. So usually you would be hearing the word not more than 1%, not more than 0.5%. Usually they're expressed like this in limits, not more than. Okay? Now, take for example, you produce this one, 100 grams of paracetamol powder. This is the weight, but not all of it is paracetamol. Some of it would be the impurities. So let's just say your purity statement is, I'm 98% pure. Then it would make sense that the remaining 2% are your impurities. Right? So out of 100 grams, 98 grams is purely paracetamol. The 2 grams would be something else. Therefore, purity is a measure of quality. How do we exactly measure purity? There's so many techniques. Some of them are really advanced, like your HPLC. But here, the reality is we still do your classical methods. Your classical methods are your traditional methods, very manual, benchtop kind of experiments. So you can see your glasswares in action. So titration is a classical method of determining the purity or amount of a test substance by reacting two substances until you reach an endpoint. One of the most basic types of titration is your acid-base titration. So you're reacting base and acid. And they have different terms, acidimetry, alkalimetry. So that will be discussed by your teacher maybe. So here, I'm just going to show you the setup. So you have your burette. You can spell it like this or like this. This is the one on top. And it will hold your titrant. So it's easy to remember, T top. You can also call it your titrant your titrator or your volumetric solution. Now, here we have another glassware. We call it your Erlenmeyer flask or conical flask. It will now contain your titrand, D for down, or your test solution. It's the one that you're trying to measure, the one that you're trying to test. It's your sample. Okay? So this is how it looks like in your laboratory. Okay? Now, just for you to be more aware of how different they are, your titrant on top is the one that you need to react with your sample. Okay? You know its identity. You know exactly what chemical you're putting inside. You know the amount that you put and the purity of your titrant. Or maybe you can call it your concentration. Basically, Your titrant is a standardized substance. You know its concentration, you know its strength, you know its purity. Meanwhile, your titrand, the one at the bottom, you know its identity. I know this is my sample. I know how much I'm putting inside in this flask, but I don't know exactly how strong it is, how pure it is. So that's what you're trying to find. Now, there's a third component. We call it your indicator. Your indicator is a chemical that will change in color. So let's just say red to blue, blue to red. And once it changes in color, you would know that the reaction is complete. We call that your end point, which will signify that the reaction is done. There are two types, visual or experimental, and stoichiometric or theoretical. When you say visual, I hope you understand you are noticing a change in color. Sometimes the endpoint is not only change in color, it could be change in temperature or maybe formation of a gas. That's also possible. But here, it's more of change in color because of your indicator. Now, you have to perform experiment in order to see this. That's why you call it experimental. How about this one? This one is using your equation. So if you know your substance exactly and you know your equation, you just try, right, to plug in the data into your equation and you should be able to solve what is an endpoint, meaning to say how much should I use so I could reach the endpoint. Okay, so there are cases wherein we do experiments to confirm the theory. Ideally, they should be close. So if the theory tells you you need 23 ml of this one to reach this one, if you experiment, if you conduct the experiment, it should be around that volume as well. They should be more or less the same. That's the ideal. If it's too far, then maybe your experiment is not really properly performed. In essence, your endpoint, chemically speaking, same amount of your titrant and your titrand have reacted. Okay, so the process of titration is really simple. Just prepare the chemicals by dissolving them in a solvent. You have to take note of its concentration, usually expressed in terms of normality. Okay, and then your flask should contain, that's the one at the bottom, that should contain your titrand. So you will be putting your titrand solution, your test solution, add a few drops of your indicator. Usually 3 drops will do, usually. And one example is your phenolphthalein, a classic indicator. Now your burette will house or contain your titrant. You should take note its initial volume, okay, the starting volume. And then once you're ready, release the burette, and then you will be dropping your titrant. If you expect your volume to be around 20 ml, then you can just open it up and wait for it to flush down. But if you're really careful, it's better for you to be slow and careful than repeat the entire step, right? So add in a few drops, swirl, 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 keep on adding until you're close to the end point. Be careful, slow down, and then once you see the sudden change, stop. Close the stopcock, okay? And then you will record the final volume in your burette. Okay, so that's exactly how you should be doing it, but maybe it's a different order, okay? It will really depend on your manual. Now, the purity equation, the percent purity equation. So here is a really good representation of how you should assign your numbers. The volume and normality are the data coming from your titrant or titrator. So you need to know the volume and the concentration of your titrator. Now for your titrand, this is the test substance. You are solving for its percent purity. Whatever substance you're trying to solve in terms of purity, you should be using its milli equivalence. It's MEQ, and then its weight. And then since it's in percent, times 100. Okay, so this is a shorthand way, just using the acronym. I like this, it's easier to the eyes. All right, so let's have a sample case. You have here solve for the percent purity of a 0.45 gram calcium carbonate if an endpoint is reached after titrating it with 55 ml of 0.1 normality sulfuric acid. Is your brain okay? Okay, I hope it's okay. One sentence, a few words, but for some it's overwhelming. So if you don't really like numbers, one tip from me is to visualize the setup. Use your visual skills and then assign. So the one on top is your sulfuric acid in this concentration, known concentration. And the volume that was consumed was 55 ml. So from here, it drained down until it needs 55 ml. Stop. Okay, that's how it plays, no, in an actual experiment. Then the one that you test, you dissolve 0.45 gram of it in a given solvent, and you want to know its percent purity. Okay, now that's very easy. You can just plug in the numbers. This is 55, this is 0.1. MEQ, you need to solve for it later. I will teach you. And the weight should be the 0.45. And then times 100, you will be getting the percent purity. Okay, but wait a minute. We acknowledge, okay, some teachers give us really easy sample cases. And then later on, when you go to the quiz, it's like times 10 harder. So I know that's possible. So we are going to try to extend as much as we can in preparation for the harder things. Okay, so this is your burette. So you start with the higher volume, right? It's a taller volume here. You can see it's up here, and then you dry, you open the stopcock, and then it keeps on going down, and then you keep on releasing and stop when the sudden change in color is observed. So you will stop here, hold, close it. Okay, so the difference between this one, obviously, and this one would be the volume consumed. Okay, and you have to be aware. Okay, this is your burette, and you would notice that the markings is what? It's increasing, right? So on the very first, this is 0, 1, 2, 3, 4, until it goes to 50. So when you try to solve for the volume consumed, it should be final minus initial. So for example, you start with the 15 ml mark. It's up here, 15 ml. And then you finish around here, the bottom, 49. So 49 is the mark, minus 15, you get 34. No worries, if you interchange them, it's still okay. You just get the absolute number. Obviously, you're consuming something, so it shouldn't be negative. Okay. How about for normality? That's the second factor that you need to use. So usually in your problems, they will just give you the normality of your titrant. But what if they don't? Whoa, what if they don't? Do you have to panic? No, you don't have to panic. Just remember these equations. Okay, this is my favorite. I have a bias. If there are so many versions of equations, I only use one equation. And the equation that I use is the one that is more versatile. So in this case, I love using this one because this simply takes your molarity times the number of factors or the number of equivalents. No, you just have to memorize, solve for molarity, and then just multiply it in the number of factors. No, what do I mean by that? Okay, let's take an example. Okay, you have 5 grams of this chemical, sodium hydroxide, and you dissolve it in 1 liter of water. So you have the volume, which is 1 liter. You are asked, what is the normality of this solution? So remember, I'm sorry for that. Normality is molarity times the number of equivalents, aka your N factor. Okay, now your molarity, if you remember, you can solve this by getting the weight of the substance, that's your 5 grams, divided by its molecular weight. So you need to know the molecular weight of this guy, divided by the volume in liters. Never forget liters. So if it's given in ml, you still need to convert to liters and then multiply by the number of equivalents. So now we take that case and try to assign the numbers. 5 grams goes here. Okay, the NaOH, the molecular weight is here. When you solve for the molecular weight, you just have to take the individual weights of the atom count the number of the atoms and then multiply, then add them up. So 1 sodium, 1 oxygen, 1 hydrogen. So your sodium is 23, your oxygen is 16, your hydrogen is 1. If you add that up, 40. So the entire molecule weighs this much, 40. Divide by 1 liter, and just 1 n factor. So question is, how do we solve for the n factor, or the number of equivalents? It's easy. If it's an acid, like for example HCl, just count the number of H. If it's a base, usually they end with hydroxide, OH. You just have to count the number of OH. So in this case, it's very obvious, by the way. 1 hydroxide, this is a base. So you have 1 equivalent. But what if it doesn't have that? What if it's a salt, right? If it's neither an acid nor a base, will you panic? Of course not. So you have to remember, one way for you to solve it is to count the number of the cation, that's the positively charged part of your molecule, and multiply that number to its oxidation state. So for example, let's just imagine this is non-existing. You only know that the first part here is sodium, and it's just 1 subscript. So 1 times 1, your Na is plus 1. So that's why 1 times 1, you get 1 equivalent. So that's why you put it here. So the N of this is 0.125. Okay, so let's make it harder. What about if we have this so this is now your salt. See, it doesn't contain H. It doesn't contain OH. You have 5 grams of that. Okay. Check for its molecular weight. So going here, you have 1 calcium, 1 carbon, 3 oxygens. So that's the reason why you have to multiply it by 3. Calcium is 40, carbon is 12, oxygen is 16, times 3, 48, add them up. This is the weight of your entire molecule. Put that in. And then remember, this should be in liters, so convert to liters. Move 3 decimal places to the left. 1, 2, 3, 0.5 liters. Okay, let's go to the number of equivalents. So remember, just focus on the cation. It will make your life simpler. But I have to say, when you go to a different kind of titration, the one that uses redox, you have to count the number of electrons transferred. So this one is the easy part. Okay, it's a shortcut, but later on you need to change this for your redox titration. Anyway, in this case, you have your cation calcium. This has a subscript of 1. Okay, so 1 times its oxidation state of plus 2, you get 1 times 2, 2 equivalents. So this is how you solve it. 5 divided by 100 divided by 0.5 times 2, you get 0.2. Okay. Okay. So your milli-equivalents, that's the third component. Here, you have to remember, this is the data coming from your sample. Okay? Not coming from your titrant. It should be from your titrand. Letter D. Okay, so here you need to know its molecular weight. No worries, you know the identity of this guy. So using the same technique before, you should get this. And the number of equivalents, we already discussed how to get this. Okay, so remember again, the substance that you're measuring in terms of percent purity, you will use its MEQ, not the one on the burette. Okay. So in our previous problem, remember, it's the sodium hydroxide. Let's try, to get its milli-equivalence. So again, your sodium is 23, oxygen is 16, H is 1. If you add that up, that's 40. And it has 1 hydroxide. That's why 1 number of equivalents times 1,000. Remember, it's milli. So that's why you have to have 1,000 here. So you get 0.04 MEQ. This is our original problem. I'm sorry I revealed the answer right away, but here's the equation. you will just assign, this is your volume times normality times MEQ divided by the weight of your substance or sample times 100. So 55, that's the volume, 0.1, and that's the normality. And then remember, this is MEQ, and the way you solve it is molecular weight divided by the number of equivalents, or the N factor, times 1000. That's the MEQ. So calcium carbonate, we already, yes, this one. We already solved for its molecular weight. So that's 100, no? Divide by 2000. So divide by 0.45 grams, that's the amount, that's the weight, times 100. You should be getting 61.11. So remember, this formula can be rearranged to solve for the other factors. So not only can you get percent purity, what if your percent purity is given, but you're asked to give the normality of your titrant? So let me grab the Jamboard so that you can see how we could rearrange it. So this is your Jamboard, and let's just write it down fast. V times N times MEQ. I'm sorry if you're quite keen on this, but I'll just not align this one with this one. I'm sorry if it bothers you. So this should be your weight, right? That's the weight, times 100. Sometimes I don't even put the times 100. I just do this later at the end. So if you want the V, you want to isolate. What if you are looking for the V and you know your P, you know your N, you know your MEQ, and you know your weight? So you should be solving this guy, right? So just remember, you have your crisscross method. So if you want to isolate the V, you have to do the crisscross. This one goes up, and this one goes down. The crisscross method. Crisscross. Some of you guys might, divide both sides, multiply both sides to eradicate, but me, I use the crisscross method. So as you can see, the percent purity is maintained on this side. Okay. Still here, because it's in the opposite side of your equal sign, there shouldn't be a problem. It stays there. But what you want to remove are the other guys. So the weight, when it crosses your equal sign, let me erase this bit. When your weight crosses the equal sign, it should be from denominator, it will go to your numerator. So your weight goes up, right? So how about them? We don't want them. We don't want you guys. So they will also cross your equal sign. So when they do from numerator, they become denominator. So now you have your N here and your MQ. Okay, gets? Now let's try to extend besides your, okay, what about you want your weight? This is the one that you're looking for. What is the weight of your substance, giving its purity is this, and the volume consumed is V given, and the normality is also given, right? And the MEQ, you can also solve for it. So you're looking for the weight of your substance. It's easy. You just have to interchange your purity and your weight. So it looks like this. The weight becomes the numerator because it crosses the equal sign. And you just have to copy all of them, right? V times N times MEQ. And then the purity goes down. Percent purity. Okay. So they just exchange, right? I'm sorry. I forgot about the times 100. Okay. But if you're doing this, you have to divide everything, this one. This will also go down, right? So once, for the volume, let's go back to volume. Once you transferred your purity, your weight, besides purity, your N down, your MEQ down, you're left with V. This one's still here. So you also need to bring it down. So it will become the entire expression here divided by 100. That's how you get your volume. volume in ml. You will notice it's too big. The number is too big if you don't divide by 100. So it will signal you something's wrong. So this is in ml. Okay, so here you just have to maintain your 100. What about the normality? So what if it's the normality that you're trying to know? Okay, I don't know the normality of my titrant, but I know the volume, I know the purity of the substance, the weight, it's MEQ. So same as your volume, okay? So let me write it down here fresh so that you can see. So if you already know how to transpose equations, you can just end the video here. This is for those people who are struggling with transposing equations. So I think at this point, I would be editing this one because I think it's easier that way. Oh no. Okay. Some of you might be really disturbed if it's not aligned properly. So let's put the P here, percent, and this is the bar, and this is your weight times 100. Okay. See, it's already aligned. I remember my teacher before, she would reprimand us and say, hey, why is your equation sign not aligned with your bar? Okay, let's just say you are looking for the not the percent purity this time, but your normality. So you want to isolate your normality on one side. So you can do the crisscross method. So your normality should be the one left here. You don't want this, you don't want this, and you don't want this. So you get the idea. Normality, the guy stays here. The percent purity is already on the other side, so no problemo. The weight goes up. So this becomes times weight. And you have to keep the bar here. And then these guys, you don't want them. They will cross the equal sign. So from numerator, they become denominator. So volume goes here times your MEQ. What about your 100 times 100? It will be left with n? No, you will also bring it down. So this guy will be gone. It will go here. Divide by 100. So the way you do this is you solve for the entire thing. And then the last step is to divide it by 100. You will be getting your normality. So this is just teaching you how to transpose. And that's the end of my vid. I think I have some sample slides for you to study. So this one, try to comment your answers in the comment section. And let's discuss. If you got it right, then I will comment on your comment and just saying if it's right or not. This is the first problem. And for the second problem, it's a bit tricky. You have acetic acid, so you have to know what is its equivalent, number of equivalents. Okay, so that's it. Thank you for having me and see you.